Okay, so let's start talking about transformers for our last 10 minutes. So we talked about transformers a little bit already in class, right after we did mutual inductance, but now we're going to talk about it in the context of delivering power to a load. So an ideal transformer has a primary side and a secondary side. And the primary side has a voltage V1T, I of T, V1 of T, I1 of T. And the secondary side has V2 of T, I2 of T. And the number of coils on the primary side is N1. And the number of coils or turns in the coil on the secondary side is N2. And then we talk about that when you induce a current, it induces this flux, and this MMF can influence the values on the other side. So the formulas that we had before are that V1 over V2 equals N1 over N2, or 1 over N, or we write that V2 equals N V1, right? Where if N is greater than 0, we have a step up transformer. If N is less than 0, we have a step down transformer. And you guys have this already in your notes somewhere else. And if N is equal to 0, we have an isolation transformer, okay? So now the new information is about the power. So the power, V1, I1 cosine of theta 1, has to equal V2, I2 cosine theta 2, because it has to obey the law of conservation of energy. So power delivered, power absorbed have to all equal. And the cosine of theta 1 equals the cosine of theta 2, which once again leads to V2 over V1 equals I2 over I1, which equals N. Okay, so this is also the same formula that we had from before, where I1 equals N I2. So when voltage is increased, the current is decreased, and vice versa. That's what those formulas show us. So the other thing we did was we looked at reflecting impedance. So an easier way to solve this problem is to either reflect the primary to the secondary side or the secondary to the primary side. And now you have one loop, and then you find voltages and currents in that. So the input impedance from the primary side is just V1 over I1. And since we have a relationship between V1 and V2 and I1 and I2, this becomes 1 over N squared times the load impedance. So the way that I reflect the load to the input side is you divide it by N squared. So everything on this page is copied from your other lecture. It's just basically a review and reminding you how to reflect from the secondary to the primary side, and then how to reflect from the primary to the secondary side. In the following circuit, a single phase load of 10 milliwatts is to be supplied by 2.5 kilovolts via a distribution feeder with a 0.15 plus J 0.1 ohm impedance. If electric energy costs 10 cents per kilowatt hour, calculate the yearly cost of supplying the line losses if the load is constant and continuous, if no transformers are used. Oh, I know. It's going to become a transformer question. So now I remember why this is here. So first we're going to do this without a transformer, and then we're going to do it with the transformer and see what the difference is. So calculate those values. And we're going to see that the transformer is going to reduce the cost. But first we need to find what it is without the transformer. All right, so you already have all of these values except for the current. So you're going to have 10 meg equals 2.5 K times I times 0.8. So what is the current? And this is actually going to end up giving you the magnitude of the current, not the angle, but
5,000 amps.
5,000 amps. And then to find the loss, the power loss, is just I squared R. Okay, so this is where we're going to start tomorrow. I'm just going to write this part really fast. The power loss is going to be I squared R, because remember we lose our average power through resistance. So it's 5,000 squared times 0.15. 5,000 squared times 0.15 is 3,750 kilowatts. Okay. Okay. All right. So at the end of class yesterday, we were finding power losses. So we had found that the power loss in the line, which is the average power, was 3,750. And I put kilowatts. I don't think that's right. Is that right? Can somebody check 5,000 squared times 0.15? Is that 3,750 kilowatts? Is that correct?
Yeah.
Yeah, that's
okay,
right.
good. Okay, very good. So then we were supposed to find the cost loss in the feeder, cost of lost power in feeder for a year. So what we're going to do, knowing that power costs 10 cents per kilowatt, is we're going to take 3,750 kilowatts times 24 hours in a day times 365 days in a year times 10 cents. And that tells us how much power we lose in the line in a year in order to supply this 2.5 kilovolts. So what does that cost? That's times 10 to the 6. All right. So now let's find the energy delivered to the load in that same period of time. Let's find the energy delivered to the load in that same period of time. So now what we're going to do is, we know we have 10 megawatts. Sorry, the cost of the power delivered to the load. So we know that the load is 10 megawatts, because that's given here, times 24 times 365 times 10 cents. Okay. So the cost of the power delivered to the load is 8.76 million per year. Are there any questions so far about what I'm doing? All right. So if we want to look at losses as a percentage of the total power, of the total consumed power, because the consumed power is really what we care about. We care about the power that the load gets. So what we do is we take 3.285 divided by 8.76 times 100. And you get 37.5%. So obviously that's not good if I am getting rid of almost half of the power just to get what I need at the output. So one thing I had mentioned to you yesterday is we're doing this problem the first time without transformers, and then we're going to do it again with transformers so that we can see that there's a way to get the same power delivered to the load, but we do it without losing so much through the line, because by losing that power through the line, then that's just basically wasted power, wasted energy. There's nothing we're doing with that. We're just throwing it away in order to get the 10 megawatts at the load. Are there questions about that? So now let's look at a different way of solving the same problem. So notice that I still have 10 megawatts and 0.8 power factor at the load. I still have 0.15 and 0.1 ohms in the feeder line, but now I have two transformers. I have a step-up transformer and a step-down transformer. So what you're going to see here is that this is what they do in real power delivery, is they use these transformers because by stepping the voltage up, you step the current down to deliver the same power. And by stepping the current down, you reduce the amount of power lost in the line, because I know that power is I squared R. So if the current is reduced, then I know I squared R will be reduced and the power lost in the line will be reduced. So what we do here is we find the new values for our current. So IF, so here we'll have N equals 50 because it's 50 over 1. And here we have N equals 1 over 50 or 0.02. So the current at the feeder line is going to equal N times the current at the load. We calculated the current at the load in the previous problem. That doesn't change because we have the same average power, same power factor. So I can just copy over this current from before, and this current from before was 5,000 amps. So now that means the current at the feeder is 100 amps. So the current here is 100 amps. Now, that value before, let's go back for a second. That value before was 5,000 because everything was 5,000. So remember, all of this was 5,000 amps. So the power lost in that resistor was 5,000 squared times 0.15. That power is now going to be 100 squared times 0.15. The power loss is 100 squared times 0.15. 100 squared times 0.15 is 1.5 kilowatts. So that's now 1.5 kilowatts compared to the loss before, which was, it's hard to, 3,750 kilowatts, right? So it's reduced by more than half. So I went from 3,750 kilowatts lost in the line to 1.5 kilowatts lost in the line. So now let's figure out how much that is per year. So that's cost per year lost. So that's 1.5K times 24 times 365 times 10 cents. So the cost of the power loss is now $1,314 per year. $1,314 per year compared to 3.28 meg per year. All right, that's what it was. 3.28 meg per year. Or 3.28 million per year, actually. Okay, so that means by doing this, we have a savings of, if you subtract those two, 3.14 or maybe about 3.2 million per year. Questions? Do this calculation again. I'm going to have 8.76 million in the denominator. But now I have to write 1314 in terms of millions. So I think that becomes 0.001314 maybe, 0.001314, because you got to change it from thousands to millions. I think that's right. So you can see it's a much less number, but somebody tell me what that number is. So this is now percentage of power loss and loss of as percentage of consumed power.
I got 0.015%.
0.015%, very good. Also percentage of consumed power. Now here's my question. Make sure I converted that 1314 into million correctly as well. Make sure that I converted that 1314 into millions correctly.
You did.
Okay, thank you. Are there any questions? One more, and I'm going to do reflection with this one because I know that Miguel had asked me about solving a problem using reflection this morning. I don't have to do reflection to solve these problems. I could always just write a KVL equation for the left mesh, a KVL equation for the right mesh, and then just write the numeric equation for relating V1 and V2, I1 and I2, and solve it. Because either way, you get 4 equations and 4 unknowns, and you can solve it. But by doing the reflection, you only have 2 equations and 1 loop, and you can still solve. So I'll do it that way this time. So first, we're going to find n. N is the ratio n2 over n1. So for this one, n is 15. So our equations are, since V1 and V2 are positive at their dots, V2 is equal to 15 times V1. Since I1 enters the transformer through the dot and I2 exits the transformer through the dot, this is also a positive relationship, and it is I1 equals 15 I2. The first thing I want you to notice is that these are opposite. It's V2 is 15 V1, and I1 is 15 I2. Okay, so I am going to solve this problem by reflecting the secondary to the primary. So I'm going to write this as one loop. Since I'm reflecting the secondary to the primary, nothing on the primary side changes. So I'm just going to copy down 100 with an angle of 0 degrees in volts. Now what happened to the units here? And I don't know if it matters, but we're going to make this volts RMS. Okay, then we're going to have 4.5 ohms and J6 ohms. And then this point right here would be V1, and that's also going to be V2 prime. That prime means the reflected V2, okay? And then that means the current over here is I1, and the current right here would be I2 prime, which once again means that's going to be the reflected I2. Any questions? Okay, so then the formula for reflecting is that RL prime is equal. So RL prime is RL over N squared, and that's from page 2 of your notes, page 2 of your notes. RL over N squared, and this is XL over N squared. So that means that RL prime is 1,000 divided by 225, which is 15 squared, or 4.44 ohms. And XL prime is J1750 divided by 225. And so that is J 3.33 ohms. Are there any questions? Now, I want you guys to write a KVL equation and solve for I1. Write a KVL equation around this loop and solve for I1. And so remember, I1 is the same as I2 prime, and V1 is the same as V2 prime. So write a KVL equation and solve for I1. 5.35 minus J 5.6 amps. Did anyone else get that?
I agree.
5.6 amps. Okay, all right. I didn't do it that way, so that's why I had to check. I did it in rectangular form. Oh, come on. I'm trying to fix this curse. So annoying. So I got 7.736 with an angle of negative 46 degrees. And I got that by doing 100 with an angle of 0 degrees divided by 4.5 plus J6 plus 4.44 plus J 3.33. Okay? Any questions? I2 is then equal to I1 over N. So we take the value we got before and divide by 15, and I got 516 with an angle of negative 46 degrees, and that's in milliamps. Okay. Any questions? So then V2, V1 and V2, we can get them by calculating V1 is equal to 4.44 plus J 3.33 times I1. And V1 is equal to 42.98 with an angle of negative 9.3 degrees. And the units are volts. Okay. And then V2 is N times V1. So that's going to be 15 times V1. So V2 is 644.7 with an angle of negative 9.3 degrees. Questions?
Yes, thank you.
Okay, so now we need to find the impedance seen by the source. The impedance seen by the source. So the impedance seen by the source is just the sum of all of the impedances we got when we reflected. But there was a homework question you guys had to do about this one time. So if you wanted to do this without doing the reflection, you would just do V1 over I1. But since we have the reflection here, we know that this impedance just ends up being 4.5 plus 4.44 plus J6 plus J 3.33. So the impedance seen by the source is 8.944 plus J 9.33 ohms. Okay, any questions? This question we're going to answer is, what is the power at the source? What is the power at the load? And what is the power lost in the feeder again? So here's an example where we have one transformer instead of two. So we have a step down transformer, but we did not have a step up transformer. So no matter what kind of transformer or none that we have, there is going to be loss in the line. So we're going to determine the loss in the line. So in order to do that, first we're going to find the power at the source. So the power at the source, and this is the complex power, is going to be V at the source, I1 conjugate. V at the source, I1 conjugate. So that's going to be 100 times 7.736 with an angle of 46 degrees. That's because it's conjugate. That's why that angle is now positive. And that power in rectangular form is 535.4 plus J, 558 volt amperes. So the power at the source. Okay, remember it's the average power that's lost in the line, but I'm finding the complex power and we will use that to get the average power. So then let's find the power, the complex power at the load. The complex power at the load is going to be V2 times I2 conjugate. V2 times I2 conjugate, where V2 is 644.7 with an angle of negative 9.3 degrees times I2 conjugate is 560, I'll put 0.516, I don't have to do the milli, 0.516 with an angle of 46 degrees. It's positive 46 degrees because it's the conjugate. And so that complex power in rectangular form is 266 plus J200 volt amperes. So remember, law of conservation of energy, power delivered equals power absorbed. So that tells you that since those two numbers are not the same, we've lost some power somewhere. And where the power is lost is in the feeder line. So we would say, and this is now average power, okay? Average power lost in feeder line is equal to 535.4 minus 266. And that power loss is 269.4 watts. 269.4 watts. This was not the only way to do this problem, though. When we did this problem a minute ago, we just found the current and multiplied by the resistance. So the other way you could do this is just take the magnitude of I1 squared and multiply it by 4.5. So I need somebody to do that and tell me, do you get 269.4? Take the magnitude of I1 squared times 4.5, and you get the same answer without going through that whole source load thing. I think that was a good exercise, but that's probably a quicker way to do this because you just take 7.736 times square it times 4.5.